I think this slide is a little ridiculous, but. So here are the steps for predicting molecular geometries. You draw the Lewis structure, determine the total number of electron groups on the central atom, determine the number of bonding groups and the number of lone pairs, and then the book says refer to table 11.1. Well, I'm not going to give that to you on an exam, right? So don't get in the habit of doing that. You could use that to check your answer. Instead of doing that, think about how balloons would arrange themselves and imagine that lone pairs are invisible balloons. A little bit of practice, and these things are pretty easy to remember. So predict the molecular geometry and bond angle of Cl and O. So what's the first thing we have to do? Lewis structure. So they're not specifically saying which atom is in the center, but we could go just based on the order that they're in. And actually it turns out that the shape will be the same regardless of which atom is where. But we'll just go with Cl, N, and O in that order. And there's got to be at least a single bond to hold those guys together. Chlorine has 7 valence electrons, nitrogen has 5, and oxygen has 6, so I think that adds up to 18. So I count my bonds: 2, 4, 6, 8, 10, 12, 14, 16, 18. I ran out of electrons, what do I do? I'm going to make a double bond. So this nitrogen in the middle has an octet and this chlorine does not. So we'll take from the rich and give to the poor, like Robin Hood, right? So we'll make nitrogen share some more with chlorine. So we'll take that pair of electrons and make nitrogen share them with chlorine. So now chlorine has an octet, nitrogen has an octet, and oxygen has an octet.
Is it chlorine with one leg and then oxygen with 2 legs? Like, I mean, 2 bonds and then chlorine one?
Yeah. So you brought up a great point. I was talking to you about how oxygen likes to have 2 bonds and chlorine likes to have 1 bond. And so, yes, we can draw this structure, but then we're like, wait a minute, that's what's wrong. Oh, yeah. Oxygen, to have 0 formal charges, we need to put the double bond on the oxygen instead. So put it over there and take a lone pair from that guy and put it over here. The good thing is, even if we didn't catch that, it'll have the same shape. That was a good catch, though. So we've got octets for everybody and 0 formal charges, which is just awesome sauce. So we look at the central atom. How many electron groups? 3, 4, 2. So the double bond is 1 group, okay? The single bond is 1 group, and the lone pair is 1 group. So 3 electron groups. What shape does 3 balloons make? It makes a trigonal planar shape, right? So it's going to be flat. That would be our 3 electron groups. But these look like 3 atoms, and I don't have 3 atoms here. One of those is a lone pair. So I'm going to erase that atom there, and this is a lone pair. One of those bonds is a double bond, so we can kind of put that in there as well. So the electron geometry was trigonal planar. What's the molecular geometry? Bent. So this is bent. It's got an angle here, right? And it's asking for the bond angle. It's not asking you to give a specific number, because the only way you could do that is to look at information about this specific molecule. If it was a perfect trigonal planar shape, what would the angle be? 120. So we think of this as starting out the bond angle here of 120 degrees. Bless you. And then is this lone pair going to cause these guys to get closer together or further apart? Closer together. So it's going to push these guys together, which is going to reduce the bond angle. It's going to be less than 120. We're not going to be concerned with how much less. Any questions?
So you don't have to be too specific.
No.
Okay.
So the bond angles that we have 180 degrees for linear. We have 120 degrees for trigonal planar. Tetrahedral is 109.5. Weird number, but there's only one weird number you have to remember, 109.5. In the trigonal bipyramid, we have 90 degrees and 120 degrees, and in the octahedron, we have 90 degrees. Okay. And those are all, they should be somewhat familiar to you from geometry. So all we're asking for here is it the perfect angle or is it less than that? Okay? Predict the molecular geometry of I3 minus. Does that ion sound a little familiar? That was on the worksheet, huh? Right? Guess what? I think it's on this next worksheet too. Okay, so what do? Well, we need the Lewis structure, right? So we've got 3 atoms. We'll connect them to each other. We have 3 iodines. They each have 7 valence electrons. A charge of -1 means I add an electron. So I've got 22 valence electrons. I had 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I've given everyone an octet and I still have a pair of electrons. Iodine is in period 5, plenty big. It can expand its octet, and so I can put that lone pair, there's not really much room here, but I can put that other lone pair on the central atom. And brackets in a charge. So you start with the Lewis structures. So the worksheet we'll be working on tonight uses the same molecules that you already drew Lewis structures for. And you already counted the electron groups and the lone pairs. Now you might want to double check that you got those correct, but you're going to take that information and then do electron and molecular geometries and angles. Okay, so this central atom, how many groups? 5. So 5 is trigonal bipyramid, right? So we've got our axial positions, and we've got our equatorial positions. So that is my attempt at drawing this shape. This could also be a child studying ballet, just the tutu is not as full. So that's the electron geometry, but we want the molecular geometry. We have 3 lone pairs. Lone pairs need as much space as they can get. Where are they going to go? They're going to go around the equator. So this is going to be a lone pair. And this one's going to be a lone pair. And this one's going to be a lone pair. What's the name of the shape? Linear. Okay. Oops. What would the bond angle be? 180 is from here. And the lone pairs are not going to affect that because they're kind of opposing each other. Drawing three-dimensional things on a two-dimensional screen or piece of paper or chalkboard or something can be tricky. And so chemists typically use these wedges. So a straight line means that bond is in the plane of the screen or the paper. This hatched wedge is kind of like a dotted line, right? That's behind the screen. And this solid wedge is jumping out at you. So this tetrahedron here, these three are in the plane of the screen. This one's coming forward at you, and that one is going behind. It takes a little practice. But like I said, I'm not going to make you draw things on an exam, right? What if you have a bigger molecule? Because there's lots of molecules that are bigger. You have more than one central atom. Then we call them interior atoms because it's not necessarily in the middle anymore. So larger atoms have more than one interior atom. And so what you do is you look at each of the interior atoms and you determine the shape of around that atom. So here on the nitrogen, this guy over here, there's 4 electron groups. So the electron geometry would be tetrahedral with 1 lone pair. So that's going to be a trigonal pyramid. And so these guys are kind of sticking out. The lone pair would be going behind. This has 4 electron groups, no lone pairs, so that's just a straight tetrahedron. This is 3 groups, so this is trigonal planar. And this one is 4 electron groups with 2 lone pairs, which is bent. So predict the geometry around each interior atom in acetic acid, make a sketch of the molecule. Now, an exam question could ask you what the geometry is around a specific atom. It's just not going to ask you to draw anything. So what I'm going to do here is I'm going to spread this out a little bit because we really need to see the whole thing. So that H3C means there are 3 hydrogens on the carbon, and then the oxygen over here has a hydrogen, and then there are lone pairs, and there would be, come on, oh, writing with white doesn't work. There'd be 2 lone pairs on the oxygen. So what is the geometry around this carbon? That's a tetrahedron, right? There are 4 electron groups, no lone pairs. Electron geometry, molecular geometry are the same. What about the carbon? Trigonal planar. There's 3 groups, no lone pairs. And how about the water? Sorry, not the water, the oxygen. That's going to be bent. So then if I try to draw this, I'm going to make a tetrahedron on the end here. That's the, oops, not there. That's kind of the hardest one. And then this is trigonal planar. So there's my oxygen, and this is over to, I'm sorry, yeah. This is a carbon, and this is an oxygen, and this is the other oxygen, and that one's gonna be bent. I don't know why I gave that a letter and not the others. So drawing it, I'm trying to put as much of it in the plane of the screen as possible, and then just show the things that are sticking out. So this could be an exam question. What's the molecular geometry about nitrogen in CH3 and H2? So when we write CH3 NH2, we are implying how it's connected. So carbon has 3 hydrogens on it. And I'll try not to be tricky about this on an exam, because I know you guys aren't used to this notation. And then NH2, that tells me there are 2 hydrogens on the nitrogen. Are there any lone pairs? Yeah, the N's going to need a lone pair. And you can count the electrons up and stuff, and that's going to be the correct correct Lewis structure. So it's asking for the molecular geometry around the nitrogen. First, you have to think about what the electron geometry is, and then make an invisible blue. So that one's going to be a trigonal pyramid. Any questions?